In this video, we are going to set up a analysis for MSC Nastran. Now, in this example, what we're going to do, we're going to set up the cylinder with these 4 stiffeners inside like you see here, and then we're going to apply an internal pressure. So this is going to be allowed to radiate or radially expand rather. Now, if we were just considering the cylinder by itself, we do get radial expansion or uniform radial expansion. But once we start adding composites and stiffeners, we start deviating from that uniform radial expansion. We still get some level of expansion, but it's no longer uniform, and I'll explain why later on in this video. Okay, now quick comment about the cylinder wall and the stiffeners. Both of these are composed of layered composite materials, so today we'll be focusing on how to set this up with either PComp or PComp G entries. The cylinder, sometimes I'll refer to that as either the skin or the fuselage, and the stiffener, sometimes I'll refer to that as beams. Let's see what else. The original request was to do this with Patron. Now, don't be misled here. What you really want is to analyze this with MSC Nastran. Now, it doesn't matter what tool you use, as long as you get an MSC Nastran input file, that's all that matters. Here in this other tab, I have a bulk data file or .bdf. This has a description of the entire model, all the elements, all the nodes, all the materials. This is all in this input file. This is your final deliverable if you work in a company or you're in research. It doesn't matter if you use Patron or some other tool. This here is your goal. As long as you can generate this, you have fulfilled your objective. So while, yeah, I can use Patron to build this MSC Nastran model, I found it a little easier to use MSC Apex. And then we are going to use MSC Apex to build the Nastran model of the cylinder with the reinforcement, the composite materials, and so on and so on. Now, another few things. I'm going to show you how to do 2 load cases. A lot of tutorials, they would just show you how to do this with 1 load case. That's easy. But then what happens when you have multiple load cases? I'll show you how to set that up. One comment about how to attach the reinforcements to the rest of the cylinder. Now, there are a lot of ways you can do this. If you're new, one of the easiest ways to do this is to use permanent glue. Well, this is not the only way of attaching the reinforcement to the cylinder. Again, this is the easiest way. And I'm assuming if you're watching this video, you're relatively new. So I'm going to show you the easiest method in this video, and then this will set you up for the future when you want to use different ways of fastening the reinforcement to the cylinder. Okay, now one thing we are going to be looking at also are the layers in the composite. So let me show you what that looks like. So let's go here and turn on the layers, or wait, let me actually zoom out first. So right now what we're looking at are the nodal plane, or the nodal plane is where the elements are. So here we have the elements, and then for each corner of the element we have the nodes. Sometimes this is referred to as the nodal plane. So here if we look at the cross section here, let's zoom in. So here we have our 2D elements when we look at it from the XY plane. But what do the layers look like? And for this, we're going to zoom in very closely. And here on the right, we're going to display the layers. Now, what I'm looking at right now is the Viewer web app. So this is called the Viewer web app. And this is included in another tool called the Sol 200 web app. One thing about MSC Apex and Patron, they don't show you the layers of the composite. So to look at the layers, we are going to be using the Viewer web app. Now, in this example, I'm going to show you at most 8 layers. So let's go ahead and turn some of this off. Let's go ahead and display layer 1. Then we have layer 2, and then layer 3, layer 4, and so on and so on. So again, we're going to set all of this up in MSC Apex. Okay, now let's go ahead and now get started. So I'm assuming you've already built your geometry. Maybe you used a CAD program like SolidWorks, CATIA, whatever it is. You can most likely import the geometry here in MSC Apex. So here, let's go to Browse. Now, MSC Apex supports a lot of different geometry types, Parasolid, Step, CATIA. Here, my geometry is available in what's called a Parasolid file. So let's go ahead and go to this directory. Here are all my Parasolid files. You could have a SolidWorks file, a CATIA file. Most likely Apex supports it. If it doesn't, export your geometry in a Parasolid or CATIA format or some other format, and then import it to Apex. Here, let's go ahead and import all these different Parasolid files. Now, we are going to do a quick check here. Let's go ahead and measure maybe the diameter. And when we look at the diameter, we get told that our units, or rather the diameter of this, is 3 meters. And this looks correct. This is the units or the diameter that I was expecting when it comes to the CAD file. Now here in the top left, if you go to Options, Application Settings, you need to select a unit system. Now here today we're using meters, newtons, kilograms. So let's go to Units and Parameters here on the left. Click on Unit Systems here. And you're going to get a big table of units. Now, what you want to use, if you're new, you want to select a unit system that has consistency in the consistency column. Do not use an inconsistent unit system today. Again, I'm assuming you're a new user. Also, if you have a deadline of tomorrow, if you have to show your work tomorrow, this video is not for you. This is very high level capabilities. They're going to take you maybe weeks or months to learn. So again, if you have a deadline that's tomorrow, I'm sorry, you're not going to meet that deadline. If your deadline is in 1 week or 1 month, then this video is for you. Now, for the unit system here, we're going to select meters, newtons, kilograms. More importantly, for the angle, I want to work in degrees. So here, let's go ahead and select this system. More importantly, the angle column has a degree symbol. This system supports degrees. When I was rehearsing this video, I accidentally selected a unit system that was dealing with radians, and that was very confusing, especially when we're defining the composite laminate. We deal with degrees, not radians for the most part. So I'll select this unit system. I'll click OK here, click OK on this box, and everything's converted to that unit system rather. Okay then. Now, when you import your geometry, you need what are called surfaces. Here, this example already has surfaces, so let me go ahead and delete all those. Now, I'm assuming that you only have solid geometry. So this is what that solid geometry looks like. Here in the axes, here on the bottom left, you can click on any one of these labels and it'll switch you to that respective plane, if you will. If you click and hold down on one of the axes, you then start to rotate the model about the axes. So here, let's click on the blue Z. That takes us to that XY plane. And now if I zoom in here, this is what I have. I have solid geometry, but eventually I want 2D elements. So I want to create what's called a mid-surface. So let's zoom out here. And let's zoom in here. Let's go ahead and click on the mid-surface tool here on the right. And let's go ahead and click. It's been a while since I've used this. And another thing, I'm very rusty with MSC Apex. I don't use these tools as much as I did every day. I'm more involved with development at this point, so you'll see me make mistakes. Maybe I'll forget where a button is. Maybe I'll forget how a tool works. So bear with me while I go through this tutorial. Okay, so here, maybe I want to use, let's go ahead and look at this. I think it was this option. So here we're going to click this second option, mid surface from single thickness solid. So we'll go ahead and select this cylinder solid. And then this will go ahead and build, here, let me go ahead and exit this tool. This will go ahead and build what's called a mid surface. So if I go here right now, what I'm doing, I'm changing the color or the rendering of the solid geometry. Do I want the faces of the solid geometry to be colored, or do I want to look at just the edges of the solid geometry? Now, here, let me do this in another way. For the solid geometry, let's go ahead and use the wireframe. So inside of the solid geometry is a new surface. So here, let's go ahead and look at that. So before we have this, but now inside is this solid geometry. Let me go ahead and rotate this a little. So here, this is the mid surface, if you will, and then now we have the solid geometry. So they're both superimposed. If you're not careful, it'll be inside the solid geometry and it looks like you didn't create the mid surface, but trust me, it's there. Now, let's go ahead and repeat this for the stiffener. So let's go ahead and hide everything else, and let's go ahead and create our mid surfaces here. So we're still using this second option. So let's go ahead and click on this stiffener. And you'll notice that I have the new mid surface inside. And let's go ahead and repeat this for this stiffener, this third stiffener, and this fourth stiffener here at the bottom. So now I have these surfaces for all of these different solid geometries, if you will. Now let me go ahead and do this. Let me show only the surfaces. So here I'm just marking the chalk boxes for only the surfaces. So here they're all in green. Here on the right, let's go ahead and click on the surface smasher. And let's go ahead and give this a mesh. So here I'm using an element size of 0.1 meters. I'll leave it up to your judgment to decide what element size to use. Now, again, I'm assuming you're a beginner, so I'm going to use a very large element size. This is sometimes called a very coarse element mesh. If you want something that is a fine mesh, you would use a smaller element size, and then you'll notice that your mesh is more fine. The elements are smaller. Here, we're not aiming for a very detailed, or rather very fine mesh. So let's go ahead and give this a moment so we zoom in. You can see we have a lot more elements. I don't recommend using a very fine mesh if you're a beginner. I recommend using something that's a little bit more coarse. And a lot of the time you can use a very coarse mesh. You still get decent results. So let's go ahead and remesh this in a quick moment. Okay, so now let's do this. Let's go ahead and create an isotropic material. Maybe this is composed of steel for now, so let's go ahead and create that here. We'll give this a Young's modulus, and I don't know what the density is for now, but we'll just assume it's 1,000 kilograms per meter cubed. Next, we need to assign the material. Now, one quick comment here. Every time you have a node, or right now we have a mesh. It's a matrix, and right now the matrix has no material or thickness, so all the columns on the rows are 0. Now that's a problem for us. We can't find a solution if the stiffness matrix has nothing but 0 values. So what we're going to do now, let me delete these old properties. We're going to define a material. We're going to define a thickness for all these 2D elements, and then we're going to assign that to the mesh. So then our stiffness matrix is not completely filled with zeros. The diagonals are 1. Some of the off-diagonal terms are non-zero. So I'm deleting these old thickness definitions that were created. Here, what happened when you create the mid surface, I believe there's an option that says auto assign thickness and offset. If you have this checkbox marked, it automatically create all these different 2D element properties, but that's not what I want. Okay, so let's do this. Let's give this a material, and let's give this a thickness. Let's try maybe 0.01, and let's go ahead and drag and select everything here in the window. And then once you do that, or rather before that, once you supply the material and the thickness here, click on assign 2D element properties, then select everything on the screen. And then here you get a prompt saying, hey, there are already thicknesses and offsets that have been defined for this. And you say, well, clear it. Just overwrite everything I said before. And then here on the bottom left, it tells you what happened. You assign the thickness to 5 objects. So we can close this. Okay, now maybe you want to look at the thickness. What does the thickness look like? Here in this horizontal bar of options, click on this option here. Click on this arrow, click on the 3D option, and then turn it off and on. And then if you zoom in, you get a preview of the thickness for the 2D elements. Now, you can adjust this thickness. It's really up to you. Just know that that's available in this tool. Okay, so let's see. What else are we looking for? I think for this first example, I'm going to perform the statics analysis with just steel. And then later on, we'll add on the composite material. So here, let's go ahead and look at what I have here. I have some offsets here. Here, delete these offsets. You don't want to be having conflicts with that. So far, I've defined the mesh. That gave me a stiffness matrix with nothing but zeros. Then I created a material, and then I gave that material and the thickness to the mesh. So now the diagonal terms, they're non-zero. Maybe they're values like this. I don't know the exact values, but I think you get the idea. Some of the off-diagonal terms are maybe non-zero also. So we're getting there. Now let's go ahead and apply the load. So here on the right, we'll go to loads and boundary conditions, and we'll give this a pressure load. Now, when you try and select an object on the screen, it's going to pick any one of the following options. On the screen right now, we have geometry and we have the finite element model. So the finite element model, what do you have? You have 2D elements, you have nodes. For the geometry, you have solid geometry, you have surface geometry. So right now, when you try and pick something, it's having to decide from all of these things what to pick. The first thing that it's found to pick is one individual element. So here you see that selected here, it's yellow. Here in this vertical option, you have the option of selecting specific objects to select. Here I say, you know what? Ignore all the elements and the nodes. Just focus on faces for now. So here I'm only selecting the cylindrical surface, if you will. Now here on the bottom left, and let me look here. Did I do this? Oh, okay. It didn't go through successfully. That's because I forgot to supply a pressure. I don't know what pressure you're looking to have. Maybe it's 100 pascals for this example. Once you select that, now you can select the cylinder surface, and now it's gone ahead and applied the pressure. Now, let me undo that and show you another way to do this. Right now, this option, this lining mode option, when you have that on, this is yellow. This is sort of a rapid option. This is going to do a lot of things automatically for you. I'm not a big fan of this option, so let's go ahead and deselect that. Let's go ahead and select this face. Now you manually click the scroll wheel or the middle mouse button or MMB, and that's going to commit the change. Whereas before, when we had the lightning bolt on, we first had to complete this form, and then we select the face, and it automatically applies the load to the object here. Here, maybe I'll leave it on, this lightning bolt option, this fast mode, I'll leave it on for the remainder of the tutorial. But if it's too much of an issue for myself, maybe I'll disable it later on. Okay, now we want 2 load cases, so I'll create a second load case. Here on the bottom left, maybe we want to temporarily hide this load, so we'll go ahead and deselect that checkbox. For the second pressure, we are going to say that it's maybe 200 pascals. So let's go ahead and change that to 200. And let's go ahead and select this cylindrical surface. And now this is our second load. And now we're done with loads. If you look here at the bottom left in the model tree, we have load 2 and then load 1. So both of those are there. Remember, we want 2 load cases at the end of this. Okay, so we want to solve this system of equations. Kx equals F. So this is going to be our column vector, our stiffness matrix, and our X. Now, there's one problem with this stiffness matrix. The determinant is 0, I believe, and that's a big problem for us, because then when you try and perform the solution, the stiffness matrix ends up becoming singular. That's a big problem for us. So what do? What we're going to do, we're going to constrain the model. We are going to constrain the model so we remove some of these columns in the stiffness matrix. So here, maybe this degree of freedom we're going to constrain, and then maybe we're going to constrain this other degree of freedom, and then the respective rows are also eliminated from the stiffness matrix. So let's go ahead and add the supports now. So I'm assuming that you're going to be constraining, or you're going to select the one axis here. We are going to constrain axes relative to the y-axis. Now, this is very important, because if you want to constrain it about the x-axis, you're going to have to use different supports. So again, we're looking at this in the x and the y plane. I'm going to put constraints relative to the y-axis. So let's go ahead and rotate this. So the positive z is going in the right direction. Let's go ahead and open the constraints here on the far right. And I'm going to disable the fast option, the lightning bolt. So here I've turned that off. It's no longer yellow. Here I'm going to select the second option, general constraint. First, I'm going to say, hey, let's go ahead and constrain the third degree of freedom for these nodes on this edge. So here in this vertical bar, let's select the geometric edge option. Let's select this one edge. Let's click the scroll wheel or the middle mouse button. And now I'm saying, hey, let's go ahead and constrain the third degree of freedom for all these nodes that are here. Now let's go ahead and create another constraint. And let me go ahead and make sure this constraint has been created. So maybe we'll zoom out. Okay, so let's go ahead and click the scroll wheel a second time. And what I'm looking for, oh, here it is. Here on the bottom left is that constraint we just created. So let's go ahead and hide that constraint. Let's create another constraint. Now this constraint, we're going to constrain this in the one direction. So this time we're going to manually pick nodes on the model. So let's go ahead and drag and drop. So there's one node here. And then we want to do this for the bottom also. So here we'll hold down the shift key, and then we'll drag and select. And then if we zoom out, you'll notice that both nodes are orange. We've selected both nodes. So if I rotate this a little, you should have a node selected at the top and a node selected here at the bottom. Then click the scroll wheel this creates your second constraint. So that's going to be here at the bottom. Now let's create a third constraint. So the third constraint is going to be for the Y direction, and then maybe we'll go ahead and do this for the top node. Hypothetically, this should also work if you apply it at the bottom node. So let's go ahead and select this node here. Sometimes it helps if we go into one of the planes. So let's go ahead and look at this. I want to look at this at maybe the YX plane. Let's go ahead and rotate this. Okay, there we go. So zoom in. And since this is cylindrical, we know that there's at least one node here at the top. And let's go ahead and click the scroll wheel, and then we've applied our second node. Now you might be asking, okay, what's a good way to make sure that the determinant is not equal to 0? How do we make sure the determinant is non-zero? Basically, you want to make sure that the sum of the forces in the X and the Y, you want to make sure that they're all non-zero. You basically want equilibrium. So let me go ahead and show you what I mean by that. So you want to make sure that the sum of the forces in the X are 0, the Y, the Z. So let's go ahead and update this. So the Y, the Z, and then the moments too. You want to make sure the moments are in equilibrium. And then bear with me because sometimes my mouse gives me a little trouble here. So you want to add enough supports such that you have equilibrium. If you have that, perfect. Your determinant is non-zero. You can actually perform the solution for this set of equations here. Okay then, so let me go into the Z Y plane again. So let me rotate this. So right now we're looking at this in the XY plane. I have constraints that prevent the motion in the Z direction. So that would be this set of constraints. And then I have the second condition. This second condition is going to prevent motion in the positive X direction. Now, the third constraint, that's going to prevent motion in the Y or the third direction, or second direction, sorry. Now, it's very important that you create these constraints correctly. Here, I assume that, hey, I'm going to apply these constraints to the Y-axis. So these are the constraints you would use. If you put constraints along the X-axis, the constraints would be a little different. So just keep that in mind when you're going through this exercise. Okay, now let's go ahead and do this. Let's do a test run. Let me save this. And one thing about saving, save often. Something might happen, your operating system abruptly stops, the power goes out. The last thing you want to do is spend hours and something happens. Here, I typically like to save every 10 or 15 minutes. Also, I like to export the geometry pretty often. So you can right click on export. And here you would do this for the model. You would right click on the model, export, and then you would export it maybe as a parasolid file. And then here on the bottom left, you get feedback saying, hey, okay, we've exported the geometry at least. Let's do this. Let's go ahead and right click on the model. Let's go ahead and click on place, or before we do that, we don't want to do this for all the stiffeners yet. We only want to do this for the cylinder. The reason I say this is because we have not attached the stiffeners to the rest of the cylinder. So that's a big problem for us. So for now, right click on the cylinder, click on place in analysis scene. Let's go ahead and do what's called a or let's go ahead and do this. Let's try and do a linear statics, or actually, let me do a normal modes analysis. I'm assuming you're new, and one of the most important rule in FEA, perform a normal modes analysis first, and I'll explain why in a moment. For the loads, let's go ahead and do this. For load case 1, we're going to do this. I forgot one very important step. Right now, all of our loads and constraints, they're separate entities. Right now, I'm going to create what's called a group, a combination, or a basket. I like to use basket. I'm going to put all the constraints in one basket. So here, I'm going to create a constraint combination or a basket. I'm going to say here at the bottom right, put all of those constraints in this basket, and click the green checkbox to apply. And we'll do that for the pressure also. I'm assuming that you have multiple loads. So here we'll go ahead and create what's called a load combination. So in this overall scale factor, we're going to say just use 1. And for the first pressure, we're going to add the pressure to this load basket. Click apply. And then we're going to create a second combination. We're going to say put the second load in this next basket and click apply. So you notice I have 2 new load combinations here. So load combination 1 has the first pressure, and the second load combination has the second pressure. So now that I have these baskets, I'll say go to loads and constraints, go to load case 1. For the constraints, I'm going to say, okay, use that first basket that contains all of my constraints. Click OK here. Now, go back to load case 1 and double check. Make sure that the selection you wanted was committed. And here I see the 4th basket was selected here. Okay, now for output, I like to turn off something called echo. Now, those who use a lot of physics solvers, it could be FEA, CFD. One thing the tool likes to do a lot, it likes to take your input file and it likes to dump it out again. It likes to copy it over to the output file. I don't want this. If my final Nastran model is 10 gigabytes big, it's going to write out the whole model again, 10 gigabytes to the output file. Here I'm saying, you know what? Don't do that. That's not what we want. So I'm going to say echo, set it to none. Do not select this option, none, default, none. It's ignored in this example, or the program ignores that selected option. Select this bottom option, none, parentheses, none. Okay, let's go ahead and look at what else we have here. Maybe in the output requests, I'm going to select the eigenvector that's already marked, and I'm going to select this option, plot. What plot's going to do is going to say, hey, put the data, put the results, put the eigenvectors only in the H5 file. Do not put it in text like you see here. Why? Because if I have 5 gigabytes of eigenvectors, I don't want that in the text file at the end. Later on, we're going to be dealing with the F06 file. And I don't want this file to be enormous. So I said echo equals none. Do not repeat the mesh and FV model. And then I said, for vector, for the eigenvector, use the plot option. So this will say, put the data results only in the H5 file. Do not put data. Do not put results in the F06 file. We don't want an F06 file that's really big, so we're going to be using the plot option. Okay, so let me look here. I've given this a constraint. I specified an output control where I said echo equals none, and my output request, the eigenvector has plot. Okay, do not click the running man icon here. Click on export BDF. Now, in my version today, I was not able to configure the solver. If you want to do that, you would go here, go to options, application settings, and then there's a Nastran compute environment. Here in this executable file section, you would go to the bin directory. So you would go to the bin directory, and then there you would select your Nastran executable. Now, I did not do this properly. I get errors when I try and do this. Again, I don't use Apex that often, so I forgot a lot of things when it comes to the tool. If you're using the student edition, I think there might be a student edition path somewhere in here. This might work. Maybe this does not work, but that's okay. You can export a bulk data file here. So now I believe that's what I did. So let's go ahead and look at that bulk data file here on my desktop. So here I'm told that this is going to perform a SOL 103 or normal modes analysis. You'll notice here for the vector output command, we have plot telling us, you know what, put the data in the H5 file. Do not write it out to the F06 file. Oh, and hey, you know all this data that we are going to write out to the F06 file? I see that you told me echo the data, none. Do not echo, do not repeat the data. So again, we want a small F06 file. We did that with the plot and echo options. Okay, let's go ahead and do this. Let me go ahead and look at the data here. At the very end, we should have our constraints. Okay, that looks good. So let's go ahead and put everything here. Let's go ahead and, there's one option you can use. Here, let me go ahead and minimize all this. If you want to run Nastran manually, you can go digging around the program files. So let's go ahead and dig around a little. Look for the Nastran directory, the bin directory. Here you see a few Nastran executable files. I forget exactly which one it is. Maybe it's this one. When you double click that option, it gives you a prompt. You select the bulk data file. This bulk data file is a description of the entire finite element model. Remember, it doesn't matter if you use Patran or MSC Apex. Ultimately, we are going to solve this with MSC Nastran. If you work at a company or you work in research, this is the one file that you want. It doesn't matter if you use Patran or MSC Apex or some other tool. This is the file that you ultimately want. Here, what I'm doing is I'm telling Nastran, hey, take that bulk data file that contains my finite element model of the whole cylinder, perform, at least for now, a normal modes analysis. Now, why am I doing a normal modes analysis? So normal modes analysis, you would use this when you're performing maybe a vibration analysis, maybe you're interested in dynamics. But one very good thing about normal modes analysis, it can tell you if you properly supported your model. So if I go here and look inside the F06 file, do this. Look for fatal message. If you ever have a fatal message, that is an error. Read the error carefully, fix the error, and try again. Here, I get 0 fatal messages. That means there are no errors with this example. If I scroll down a little, one good way of telling whether or not you have an unsupported structure is by looking at the natural frequencies. So that would be here. If your natural frequencies are ever small, so say you have something like 0.8 or 12. So this is 0.0000, so many zeros, and then 41 or 67. If your natural frequencies are very small, that's indication that your structure is not supported properly. Let me undo this. Here I get 4.12 hertz, 4.75. Great. I think anything greater than 1 times 10 to the negative 6, if you have something greater than that, that means your structure is properly supported. So if you have something like 3, 2, 5, you have something like 20 or 3 or 2, that's okay. But if you have something like 7 or 8, that might be an issue that's worth looking into. If you have something like 12 or 16, that's a big problem. So again, if you have something like 400 hertz, 600 hertz, that's okay. If you have 4,000 hertz, that's okay. 40 hertz, that's okay. 4 hertz, 0.02 hertz, that's okay. But as you gets smaller and smaller, that becomes an issue. So I think generally, around, if you're greater than 1 times 10 to the negative 6, that's okay. But if you're less than that, that's a big problem. So if it was this, that's a problem. If you have something like that, that's okay. If this, sometimes that's okay. But here, let's go ahead and do this. We had 4 hertz, 6 hertz, 12 hertz, and so on and so on. So this is telling me that the model is properly constrained, so I can carry on. Now let's go ahead and do this. Let's go back here and let's work on the stiffeners now. So let's go ahead and hide this. This is now where we attach the stiffeners to our model. So we are going to use something that's called glue. Here we'll click on this interactions button, and then we click on the interaction button here. Here we're going to select the connector type. We are going to select interaction again. And then here, let's go ahead and do this. One very important parameter here is going to be this pair detection tolerance. If you remember, this cylinder has a diameter of 3 meters. Let's suppose I use something very small, 0.01 meters. If I try and select objects here, that detection distance is so small that it's not going to be detected. So let me try and show you here with an actual example. So let's go ahead and select this. And let's do this. Let's draw a small sphere, if you will. So this sphere, we're going to say that this sphere is, what did we say it was? A 1e negative 4. You notice that these spheres do not intersect. They don't overlap. So the algorithm is not going to detect contact. What if we select a bigger contact distance? Here, let's go ahead and measure the distance between the stiffener and this diameter. Here we get it's 0.02 meters. So what does 0.02 meters look like? Let's go ahead and draw a sphere here. So this is going to create a larger set of spheres, if you think. It's not exactly spheres, but this is one of the best ways I have of explaining the contact detection distance. So imagine we have 2 spheres here and here. This is 0.02 meters. When you do this, guess what? The spheres overlap. So contact is detected. So contact ... is detected. So detected ... So here, when I was going through this exercise, I think I really like using a contact distance of 0.03. So what I did here was I measured the distance. Here it told me it's 0.02, and then I said, you know what, I'll round it up to 0.03. So let's go back here and use that contact distance. So here, 0.03. And we'll go ahead and select that as my contact distance. So one benefit in using this, oh, and another thing, here on the left, I'm going to turn on the mesh. And I'm going to turn on another mesh. Let me see if I can get this. I want to show you this flickering that sometimes happens. Okay, so you see this flickering here. It doesn't know if it wants to be green or the color gray. So you see this fuzziness. What's happening here is that you have 2 faces right on top of each other. So since they're right on top of each other, the graphics device is having to decide what color the pixel should be. Should it be green or should it be gray? For the same point on the screen, it sees that, hey, there's a green surface and a gray surface at the same position, same location. And then it's having to decide, okay, here I'll show gray, here I'll show green. So that's why you have this fuzziness. For other locations like this green region, there's only one color there, so it doesn't have to flicker there. But here, just know that's why it's happening here. You have two faces on top of each other. You might have a quadrilateral element there, and you might have a geometric surface there. And then you have the color of the contact surface, which is purple or gray. So you have all these surfaces right on top of each other, and it sometimes leads to this fuzziness that you see on the screen right now. So one thing to alleviate that issue, here in the model browser, you can deselect the visibility for the meshes, and that kind of eliminates, but it doesn't completely remove the issue. Here in purple and gray are going to be the contact regions. This is where we're attaching the reinforcement to the rest of the cylinder. Now, here, another tolerance that you want to modify, the contact tolerance. This contact tolerance is automatically determined, but here, since we're switching from a steel material to a composite later on, that causes issues. So here I'm going to say, you know what? I know exactly what contact distance I need to use. Here I want to say use spheres that have around this dimension, so 0.03. Use that to detect if these two parts are within touching of one another. So let's go ahead and redo this. Let's go ahead and delete the old interaction. So here on the left, let's go ahead and right click on that and delete. And let's go ahead and select these two objects, the stiffener and the cylinder. And now I get my new contact pair. And then I'll repeat this for the top, the bottom, and the other stiffener. And then let's go ahead and close this. And here on the bottom left, we should have new interactions. So let me look at, here. So we'll click on the interactions branch. Let's go ahead and look at maybe interaction 2. Let's make sure a few things happen here. Number 1, make sure that the contact tolerance is 0.03 meters. It's within that gap that we measured a moment ago. Okay, now I like to go ahead and randomly pick some of these interactions just to double check that we have our desired contact tolerance here. And remember, we're using the manual tolerance here. Okay, now what I can do, let's see if this will work. I can go back to my study tab. Let me see if I can adjust the model representation. So I'll right click on that and I'll say associate model rep. And let me see if this will work. Let me see if I can modify this. Okay, maybe I have to click OK. Okay, that's what's going on. So here I'm going to take my existing scenario and study. I'm just going to add these parts one by one. Oh, I guess I can't do that. That's not good. I guess I have to repeat the creation again. Okay, so we have to delete the old study we created a moment ago. Before, what I did was the following. I right clicked on one part for the cylinder and then I clicked on place an analysis scene. Now what I'm going to do is say, you know what, take the entire assembly, place that in the analysis scene. Let's go ahead and run a normal mode analysis. Let's go ahead and do this. Click on generate a simulation scenario. So that was this button. And now we get a new study here, or a scenario. We have configured this for normal mode, so let's do this. For the first load case, let's go and select that basket of constraints. So click OK. For contact glue, one thing I forgot to do is I need to create a basket for the interaction. So here, the basket is called a contact table. So here I'm going to say, you know what? Select all of those contacts, put them in this basket. So I mark the checkboxes, click apply, close this, go back here on the left, double click on contact and glue. And if you accidentally are modifying this, press escape, double click this icon, go to load case 1. Here, let's go ahead and select this option, select contact pairs or tables. Select this contact table. Select this basket. Click OK. Go back. Triple check, double check, check as many times as you need to make sure that selection has been made. It's very common in these tools that if you forgot to click OK or apply or something happened, it didn't commit the change. So then you're kind of scratching your head asking, okay, what happened? Here, let's double check and make sure I've selected the basket with the constraint. So constraint combination 1. Let's go ahead and make sure the contact is there. Okay, perfect. Now let's go ahead and do this. Let's go ahead and modify output control. Let's go ahead and select the scenario. We'll say, you know what, for echo, do not repeat the input file. I don't want all the nodes and quadrilateral elements repeated in the F06 file. Now for the vector, let's go ahead and select that row. Let's mark the plot checkbox. Do not write out the eigenvectors to the F06 file. Write out the eigenvectors to the H5 file. Okay, let's go ahead and output a bulk data file. So we'll call this model B stiffeners. And then we'll go ahead and click export. Let's go ahead and minimize this, and then like before, go to the bin directory, or if you have the desktop shortcut, double click the bulk data file, and let's go ahead and run Nastran. And now one very important thing that we always need to do, we need to make sure that there are no errors in the F06 file. So we'll go ahead and give this a moment for it to go ahead and compute the natural frequencies. Okay, it sees that it's done. Okay, let's go ahead and do this. Let's go to the very bottom and let's make sure that we see this. End of job. Now let's go ahead and look for user fatal message. Click find all in the document. Now I get told that there are 0 errors. Let's look at the natural frequencies. Okay, good. I still get non-zero natural frequencies. Oh, and that was the other thing I should have mentioned. So if you get something like this, -12, if you get a value like this, it's basically 0. If you have something like this, maybe, it's basically 0. So if your natural frequencies are very small like they do here, that's a problem. This is telling you that something, it could be the cylinder, it could be the stiffener, something is not supported properly. But here, let me look at what the natural frequencies were. So here I get 4 hertz, 6 hertz, 12 hertz, 19 hertz, and so on and so on. So these are positive natural frequencies. They are not 0. This is good for me. This is telling me that I've properly supported my structure. So let's go ahead and do this. Right click on the scenario, attach Nastran results, click on browse, go to that directory where you have the H5 file. This contains your eigenvectors. If you're performing a statics analysis, it will contain your stresses, your applied stresses, your strains, and your displacements. Here at the bottom left, it tells me attach Nastran results successfully. Here in this bottom horizontal bar, click on the color cube, if you will. This goes into post-processor mode. And we're going to look at some of the natural frequencies. Now, if you had a 0 hertz natural frequency, that means something is not supported properly. When you animate the mode shape, let's suppose you had a 0 hertz or something very small, something like this 1.0 e -12 hertz, something very, very small. Remember, this is effectively 0.0 hertz. You'll hear a synonym for this. It's called a rigid body mode. What happens there is the following. When you animate the mode shape, it's going to either translate vertically, horizontally, in and out when it does that, say you had no supports, it's going to roller skate all over the screen. You're going to get those rigid body modes, 0 hertz. That's what the mode look like. Here, this is what it looks like when you've properly constrained your model. You can see that this mode, it's not bouncing all over the place. It's pretty well supported here. So here in this horizontal bar, all the modes, here in this bottom left, I can click on these arrows. I can jump between the different modes and say, okay, this structure looks like it's properly supported. I have non-0 hertz here. Let me close this. Now let's do this. Let's go ahead and try and perform a statics analysis for those 2 load cases. So let me do this. Let me delete the old scenario. I don't want to confuse ourselves with all this information, so I'm going to delete the old scenario that was for normal modes. Now let's try and perform a statics analysis. So right click on the assembly called Model 3 here, place in the analysis scene. Oh, something glitched here, so let's go ahead and. So once you do that, you have some options available here. Click on button number 2. This is going to create a new scenario for a linear statics analysis. Now, let's double click on loads and constraints. And first, let's create a second load case. So here in the loads branch, right click on that and click on add subcase. Click OK. I have load case 1 and 2. Here, if you move a little higher, select the load case 1 here. We've added the constraint or the basket of constraints. Now, what about the load? Now, you could select the individual pressure, but if you have multiple loads, they are going to be contained in these baskets. So I recommend using the baskets when you're putting and assigning the basket. Here, what we're saying is take this basket of loads, assign it to load case 1. Click apply. Now go to load case 2 and do the same thing. So for SPC, we're going to select the same basket of constraints. And for the load branch, we're going to select the second load combination, the second basket. Click apply. Click OK. Now remember, triple check your work. Go back there, go to load case 1, open the branches, make sure that your desired selections were committed and honored. Sometimes it doesn't honor your selections, so you have to redo the whole thing. The load case 1 looks okay. Let's look at load case 2. Okay, the basket of constraints is assigned. The basket of loads is also assigned. Okay, so that looks good. Now, for the contact and glue, you could do this one by one for each load case, but here, let's just go one level above that. Open the B contact, and let's select the select contact pairs or tables. We're going to select this basket of contact interactions, if you will. Click apply. And now, since we did this above all the load cases, whatever was done above all the load cases is inherited by all the other load cases. So here in scenario or at the above subcase level, above all the load cases, we define the contact definition that gets carried over to load case 1 and 2 automatically. So even though if you look here, let's deselect this and click apply. Even though load case 2 does not have a contact definition, even though load case 1 does not have a contact definition, since we went at the highest level possible and there we defined our contact, that's going to be inherited by any lower level subcases. So let's go ahead and click OK there. Go to output. Let's go to output control. And for echo, remember, we don't want to repeat all the bulk data file entries, so click OK there. Now, you know that you forgot something when you have a gigabyte or an F06 file that's maybe 1 gigabyte big. That's because you forgot that echo equals none, or you forgot to say, hey, oh, I think this is done automatically for the displacements and the stresses, right? So since we're doing a statics analysis, here it's automatically selected the displacement and the stresses. You'll notice that plot is already selected here for these options, so we don't have to worry about the plot here. It's already been done for us. Okay, let's go ahead and save this. So here, Control S, and let's go ahead and output this. So we'll call this model B stiffeners, stiff for short, statics, and export this. So let's go ahead and let's run Nastran now. Now you want to do this incrementally. You don't want to do this, how do I say, all in one go. Some of you might be tempted to say, okay, let's put the composite material on. Let's put in the stiffeners. Let's attach them. Let's put everything on the first analysis. That is the wrong way of doing it. You're going to be getting yourself very confused when it comes to this whole process. Do this in pieces. First, analyze the cylinder. Once that's good to go, let's add the supports, then the loads, then the material. Do this incrementally. Don't do this all in one go. Do your normal modes analysis. Make sure you're supporting your structure properly. Okay, now let's go ahead and look at the F06 file. Let's search the file for any user fatal message. There's another rare one called system fatal message. So if you want to look for both, just look for fatal message. Okay, now one value that I like to look at here is the external work. If you get a value here that's telling you that there is deformation in your model. Now let's go ahead and do this. Let's right click on the scenario and attach the results. Let's go to browse. Let's go ahead and do this for the statics H5 file and click attach. Let's look at our displacements for this statics analysis. So we'll go to post-processing mode. Now we want to confirm one thing. Do we get radial expansion? Now, this worked if you only consider the cylinder. This may not work if you include other things like the stiffeners. If your composite material is asymmetric, this won't give you radial expansion. So here, let's go ahead and look at this view. Now, right now the loads are being superimposed on the model. That would be these blue arrows. Here in this horizontal bar, click on this right icon or button. Here, click on this button. This will turn off the loads and boundary conditions. So here you'll notice that we do not get a perfect or uniform radial expansion. Here, because we added the stiffeners, this is giving us a non-uniform radial expansion. You notice that even here on the left and the right, the expansion is a little different. Again, if we were just analyzing the cylinder wall, we would get uniform radial expansion, but once you start adding all the stiffeners and materials like composites, it's no longer uniform. But what's important here is we do get this radial, or not radial expansion, but we get expansion. So let's animate the deformation. Let's slow this down. So this bar here at the bottom, this controls the speed of the animation. So you can see that we do get that expansion that we wanted. If you wanted to, you can click on this fringe button and you can look at the stresses. Okay, so what's there left to do? It's time to focus on the composite. So let's go ahead and do this. This is going to get very complicated. So if you want, feel free to pause the video here, take a break. And now let's go ahead and start talking about composites. Let's go ahead and hide all of our solid geometries. So you notice one thing. I'm always having to turn off the solid geometry. There is another way to do that. You can use these tools here at the bottom or the top horizontal bar. If you tell it, you know what, just completely hide all the solids. That's permanent. It doesn't matter what you do here in the model tree. This top horizontal bar will permanently hide that object. If you want to permanently hide the 2D elements, that would be this icon. If you do that, now all the 2D elements are hidden. If you want to hide all the 2D surfaces, now they're permanently hidden. Here, let's go ahead and show the 2D elements and the 2D surfaces. So right now, I've permanently hid the solid geometry. Now, what about the loads? I believe they're not marked here on the left, right? So you notice that the loads are not displayed because I marked the check boxes. If I want to permanently hide the loads, I can click this icon. And it doesn't matter what you do in the model tree. Since you permanently disabled the option, they're forever hidden. But now if I click that button again, they're not visible. So let's go ahead and do this. Let's disable the options here on the left, and let's permanently hide the loads because we know the loads are already properly configured. Okay, so let's do this. Let's recolor our surfaces. For some reason, they're all having the same colors. I don't want that. So let's go ahead and do this. Let's see if this will work. I'll give this an orange color. I'll give this a blue color. I'll give this a green color. And then I think, maybe that color was not ideal. Okay, now we gave everything different colors. So this is going to help us differentiate all these different parts a little bit better. Okay, now let's talk about element coordinate systems. So there's a very big problem that I see new users have, and that's with the 0 degree direction for composite laminate. So here, 0 degree direction. That is very important. You have to know which direction is your 0 degree direction, or you're going to be doing your work completely wrong. Let's do this. Let's draw a mesh. And let's draw some maybe rectangular elements, some triangular elements, and a few more here. Now, I'm assuming this is already meshed and we're just focused on a few. There's something called the element coordinate system. So this XE, YE. And then here has its own element coordinate system, XE and YE. This is a very big problem. There's a second coordinate system called the material coordinate system. Now they're both identical when you first start out. So this is XM for material coordinate system, YM. And then this is XM and YM. Now for this element, I'm going to skip showing you the element coordinate system. I'm just going to show you the material coordinate system. So this is the default. Now this is a big problem for us because for this element, this is the 0 degree direction. For this element, this is the 0 degree direction. For this 2D element, this direction is a 0 degree direction. So you see the incompatibility here. It's very important that you know which direction is the 0 degree direction. So here, let's do this. In this horizontal bar, you have some options. You can display the element coordinate system here. So you get told, if you zoom in very carefully, you get told that the red axis, this is the X element axis. This is currently the 0 degree direction of your laminate that we'll build in a moment. This is the 0 degree direction that runs along the circumference of the cylinder. We are going to say here that, you know what? I want my 0 degree direction to actually go in this direction. I don't want it to go along the circumference. I want it to go in this direction. So we're going to manually modify what's called the material coordinate system for each element. So let's do this. Let me create a new one. Maybe I'll save it here. So it so happens that for this example, all of the elements are aligned. So let me draw the X element axis. So I think it looks something like this. This was my XE, my YE. And then by default, the material coordinate system is also equal to the element coordinate system. So let's draw that. And then this would be my 0 degree direction. So then here, this would be my XM, and then this would be my YM. And then I'm sorry if I get the labels mixed up. I do that sometimes. So this would be the 0 degree direction. Now here, I'm going to show you how to manually modify this material axes. Here, what we're going to say is that, hey, you know what? Flip these. So this is going to be my XM, and my XM. So we're going to flip this so all the 0 degree directions go along the horizontal axis, which happens to be the Z axis. Now, another thing when it comes to the 0 degree direction, or a laminate rather, we need to know what the stacking direction is. So suppose we have a 2D element. This is going to be, let's look at a C-quad element actually. So let's look at this C-quad element here. Let's say this is node 101, 102, 103, and 104. So that's what the 2D element looks like right now. So this is a 101, 102, 103, and 104. So this is currently the order in the 2D element here. If we use the right-hand rule, we go in this direction. So this is going to be what's called my positive Z element direction. So now that we know which direction is the positive Z, how are the layers in the composite stacked? This is going to be layer 1, layer 2, layer 3. Layer 1, 2, and 3. Oh, I messed that up, so let's do this again. 3. Dot, 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 however many layers. Now, let's suppose if I reverse the direction. So now, instead of going in this direction, what if I go in this direction? So this is going to be now defining my positive Z in this direction. So then how is this stacked? This is layer 1, 2, 3. So 1, 2, 3, dot, 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 until your last layer. So then here on this entry, how do we do that? It's simple. Just reverse the order of the element or the node IDs here. So we flipped the direction of that positive Z element axis. Here in Apex, there is a way to look at this axis or this vector. It's called the shell normal. So here we go back here. This is called the shell normal. So this is the positive Z element axis. This is going to tell you how you're going to put your layers. So let me take a screenshot of this. And let's look at this here. So here we get told that my normal direction is in this direction. For the stiffener, I get told my direction is in this direction. So for the cylinder wall for now, let's talk about the layers. This is layer 1, layer 2, layer 3, so on until layer N. So this is layer 1, 2, and 3. Here for the stiffener, I get told this is layer 1, 2, dot, 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 until layer N. So 1 and 2. Now what about this vertical branch of the stiffener? We get told that this is the positive Z direction. this is my normal direction. So this is layer 1, 2, 3, dot, 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 until layer N. So now when we look at this, we'll notice one thing. We'll say, you know what? I want all of this to be in the same direction. So let's take another screenshot. We'll say, you know what, for the wall, I kind of like this. I like this is layer 1, layer 2, dot, 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 and I want this wall to also be in the same direction. I want this to be layer 1, 2, so on and so on, dot, 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 until I get to layer N. So what we need to do, we need to take this shell normal and we need to flip it. We need to reverse it. So it's in this direction. So if you recall here in the 2D elements, we need to reverse the order. And you might be asking, oh wow, we have to do this for every element? There are millions of elements here. Apex has a simple way to do this. Here, if you go to the meshing, or the mesh fem edit rather, if you go to element orientation, there's an option here called reverse orientation. So you select that option. Let's go ahead and in this vertical bar, let's pick only the faces. Let's pick the cylindrical face and maybe, yeah, let's pick the cylindrical face. Do not pick any of the stiffeners. Pick the cylindrical face, and I think right now it's currently set to pick individual faces. So let's go and look at this. Right, so be very careful with this. So even though the stiffener is one surface, so here, this is face 1, face 2, face 3, 4, 5, and 6. All 6 faces are connected to each other. I know they're connected to each other because this edge is green. If it's green or yellow, the faces are connected. If it's red, it's not connected. So if you look here, this edge is unconnected to anything else. But these faces are connected to each other. So that was the sidetrack. Let me go back here. So be very careful when you pick on these faces because you think you're picking the whole stiffener, but you're actually picking individual faces. Here for the cylinder wall, let's go ahead and pick that. So just click that. It turns orange. Press and click the scroll wheel, and it'll flip the normals for you. So this might take a while. So let me move this to the right. So here, remember, it's going to reverse the order of the nodes. And if you look at the finished product, you notice that the normals have been flipped. So you can think that layer 1 or ply 1, layer 1 is going to start here, layer 2, layer 3, dot, 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 until layer N is up here somewhere. Okay then, so we now know the direction that our layers are going to be stacked. Now let's work on defining the 0 degree direction. Let's go ahead and create what's called a coordinate system here. Let's turn off the normals for now. And let's do a quick save. We are going to discuss what are called Euler angles, because this is going to be very important when we talk about coordinate systems. We are going to tell Apex to build coordinate systems using something called Euler angles. We are going to be using Euler angles using the 3-1-3 direction or method of rotating our coordinate system. Now be very careful, because when you look online for more information on this, it's very important that you know which system they're using. Some will use the 1-2-3 method. Some others will use a completely different way of doing the rotation. So just know that when we're using Apex to define our coordinate system, so here on the right, let's define our coordinate system here. Here, it doesn't tell you right off the bat which system is being used, but if you click on the workflow instructions, here in the tip 1, it tells you exactly which approach they're using. Here it tells us that we're using the 3-1-3 approach. So what does that mean? let me do my best to explain what this means. So maybe let's go to Paint and create a new document here. So let me do my best here to tell you what that is. Okay, so we have this initial coordinate system called X, Y, and Z. So that's the starting point for our coordinate system. We give it Euler angles. We say rotate this 90 degrees, then rotate it by 0 degrees, and then rotate it about 90 degrees using the 3, 1, 3 approach. So what does that look like? So the first rotation is going to be 90 degrees about the Z axis. So here, let's redraw our coordinate system. So you'll notice that our x-axis is going to swing. So this is going to be the new direction for x, the new direction for y, and the z-axis remains up here. So we swung this about the z-axis by 90 degrees. Now, in the next rotation, it's about the y-axis. It's going to be rotated 0 degrees, but here let's make this a little complicated. Let's say we're going to rotate this 90 degrees. So then here, what happens after that? So we're going to rotate about this blue axis here. So you can think that the z-axis is going to rotate in this direction. So let's update our coordinate system. So it's going to look something like that. So the x is still going to be here. And sorry if that looks like z. Let me draw this a little better. So this is x. This is now z or zeta. And this is now y. And now what about our last rotation? About the z-axis. So here we're going to go and rotate about the z-axis. So what does that look like? So this is going to swing the x-axis in this direction. So let's update our new coordinate system. So if I draw this, let me look at this. So this is now the x, the y, and the z, zeta, or z. So this is our final orientation of the coordinate system. Now, remember, when you go and research Euler angles, make sure you look for the 3-1-3 option, because it's very important that you are consistent. Some are using the 1-2-3 or the 1-3-1. You could really pick. Here, there's a table here that shows you a lot of different methods. So 1-2-3, 2-3-1. Do they even have 3-1-3 here? Oh, they do. Type 2, 3-1-3. So it's very important that you know what orientation or what sequence you're using. Here we're using the 3-1-3 approach. So here, I want a coordinate system that has a z or x-axis along this direction. So what do? I think it was 90, 0, 90. So let me look at what we have here. Maybe that was not correct. So let me look at this. Maybe I didn't do this right. Oh man, what's going on? I know sometimes when I click it accidentally makes the I think it's trying. Oh, okay, here we go. Here, I think what it tried to do, it tried to create the coordinate system. So let's do this again. This is what I want. This is my current coordinate system. So let's go ahead and rotate this so I get what I want. I believe I just need to rotate this negative 90 degrees. So let's try that again. And let's go in tab. Okay, I think that's what I want. So let's go ahead and confirm the position. So here we'll put this coordinate system at the origin and we'll press enter. Oh, and it's still not what I wanted. So let's undo that. I think if I press Control Z, or I could just press escape here. Now bear with me while I get the bearings of this again. I don't use Apex that often. Okay, so here. Okay, so let's try doing this. Let me rotate this. Let's say we want to rotate this by 90 degrees. And let's go ahead and give this a position, press enter there. Okay, so now what do we need to do here to get the red axes along this horizontal direction? So we know that the next rotation will be about the one axis. So let's go ahead and look at this. So let's go ahead and give this 90 degrees. Let me see if that will work. Okay. So almost. And now let's go ahead and rotate this another 90 degrees. Okay, there we go. So you see that this red axis, this is the x-axis of this new coordinate system. So now I press apply. And now I get a new coordinate system here. Now, let's create a second coordinate system. So we know that it's 90-90 at this point, 90-90. And let's click the scroll wheel. Let me see if this works. Let's left click on this. Okay, now I get this. Let's put this at maybe 1, 1, 1. And maybe I don't like that, so let's press escape. Let's retry again. So it's 90-90-90. Let's left click on the screen. Let's pick maybe 5, 0, 0. And then press the scroll wheel to commit that. Now, it doesn't matter where you put the, well, for the most part in this example, it doesn't matter where the coordinate system is. All we want is this red axis. We're going to say, you know what? All the material coordinate systems are going to follow that red axis. That's eventually what we want. So let's go ahead and save here. Let's now focus on creating our first stack, if you will. So let's go ahead and start creating our composite material. So we need to define what's called a orthotropic material for our ply or layer. Instead of using ply, I'm going to use layer. So let's go ahead and find that mat 8. And then here, I don't know what your mechanical properties are for the layer. So I'm just going to use some I'm making up on the fly. 0.3, and then my density, where's that at? Here. So these are not realistic, but I just need something for today's tutorial. I'll leave it up to you to know what your mechanical properties are for a composite and plug those in here. Okay then, so when you do this, let's go ahead and call this layer A as an example. Or I shouldn't call it that. Let me think of carbon fiber. I know a lot of you are using carbon fiber, so I'll call this carbon fiber for now. Okay, now that we have this orthotropic material that's using the mat 8 entry, let's do this. Let's create what's called a stack. So first, let's create a sheet. Let's select that carbon fiber material that we defined that's using completely wrong properties, but we'll assume it's correct for now. And then we'll go ahead and give this a thickness. We'll say this is a 0.125. Here, let me double check it a quick moment. And here, these are going to be in, well, here I plugged it in as 0.125 mm for millimeters, and Apex has automatically converted that to 1.25 times 10 to the negative 4 meters. So always watch out for units here. Okay, now create the stack. Now what I'm going to do is the following. Eventually we want to use angles of 90, 45, and so on and so on. But just so you know the stacking direction, I'm going to give this an angle of 1. Or actually, there we go. So let me create a few layers here actually. Let me create 8 layers. Oh, and a quick comment here. If your thickness is too small, you will get a lot of errors when it comes to the glue contact. So when when you have the attachments here with permanent glue, when I tried this example, if I used only 4 layers, the thickness of these sections was too small and there were issues detecting the contact. So do not use 4. Here, let's go ahead and look at that point. Right, so when my total thickness was this, it caused issues with the contact algorithm. But I think when I use 8, when I use this thickness, the contact algorithm worked properly. So make sure your thickness is not too small. So let's go ahead and 4, give this an angle. Now, again, in the end, we're not going to use these angles. The reason I'm using this is because it's going to help me communicate the stacking sequence later on. So let's go ahead and give this an 8. Okay, carbon fiber and the thicknesses. Stack is not symmetric. Okay, let's close that and reopen it. Okay, the reason I closed it and reopened it, I wanted to make sure that the definitions were here. Again, sometimes you configure something, maybe you forget to click OK and apply it, and when you go back, you realize, hey, it's not even there. Let's now go to attribution. Now, we have the stack. We need to define the material coordinate system. So the order is a little messed up here, but hopefully you follow along. Click on attribution and click on material orientation field. We're going to say, you know what? Pick the cylinder and tell it to use the x-axis of this coordinate system to orient the material coordinate system. So let's go ahead and select this coordinate system and it'll do it automatically. Okay, now let's go ahead and double check this. I believe if you click this one time, I don't think it did show you. Let me escape this. When I was preparing for this tutorial, oh, there we go. Now this is what I wanted. I wanted to show you what the new material coordinate system is. So if you remember, the old material coordinate system was parallel to the circumference, or rather, the old material coordinate system was following the element coordinate system. That's completely wrong. You don't want that. If you remember the square example where we had elements in different directions. Oh, this is a triangle. Remember that there's an X, there's an element coordinate system rather, and by default, the material coordinate system is parallel, which is not good. So this is XM, YM, and this is very important when you look at your applied stresses and applied strains, because those will also be bad. This is completely wrong in my opinion. So here we get told this is the 0 degree direction, and here this is the 0 degree direction, which is not good. What we did here with the material orientation field, we said, you know what? Take all the material coordinate systems for each element, make them parallel to this coordinate system. And we'll do that for the stiffeners again. So let's go ahead and close this. Let's go ahead and hide the cylinder. And now let's go back to the material orientation field. And we'll say, you know what? Let's go ahead and select all of these. Now, one thing that I don't like about this tool at the moment, it's not showing me what the current material coordinate system is. Here, what I have to do is I have to display the element coordinate systems, and this is telling me the material coordinate systems. Remember, by default, the material coordinate system for each element is parallel to the element coordinate system. So here, let's go ahead and do this. Let's go ahead and open this. And actually, I think I can do this for individual elements. Yeah, so let's try that. So I'll say pick this element. Here, let's turn off the fast mode. Let's pick this element, hold the shift key, pick this element and this element and this element. And then I'll say commit. And let's go ahead and look for this other coordinate system. Let's use this second coordinate system here. And let's see if this works. Okay, now I have 4 elements have been selected, 1 coordinate system. Click the scroll wheel to apply. Oh, great. Now I think I forgot. Let me undo that because I forgot which elements I selected. So let's focus on this green section. So right now, all of the 0 degree directions are going in this direction, but let me manually, purposely let's purposely make a wrong selection here. Okay, so now look at this. Oh, I didn't do it. Okay, let's do this again. Let's pick this one, and this one. Let's press the scroll wheel. The elements turn purple, indicating you're targeting those elements. Let's click this cylinder or coordinate system here. Let's press the scroll wheel again. Oh, it didn't do it. I purposely tried to make a wrong configuration here, but I think Apex rejected the configuration. What I was trying to do is do the following. I was going to purposely make this element coordinate system or material coordinate system go in this direction. So this would be the X and the Y. And what I wanted to show you is that, hey, all of the material coordinate systems here are going in this direction. But if you try to orient it in a different way, this element is completely wrong. Now, this is a problem because when you look at things like your apply stresses and maybe the one direction, the one direction for this element might be in this direction, but the direction for this other element is in a completely different direction. So it's very important that you know the 0 degree direction. Just to sum it up, sorry if that was a little convoluted. Okay, so let me go through this real quick. Let's select all of these. Oh, I didn't want that. Let me go back to the surface or the face selection option. Let me select all of these. Press the scroll wheel and use this coordinate system. And you'll notice that overwrite. And let's see if we can show you the new material coordinate system. It seems like I have to exit the tool and come back. Okay, yeah. So before, for this stiffener, the 0 degree direction was in this direction, but we say, you know what? Use the x-axis of this coordinate system. Align the 0 degree direction along this direction. Remember, the 0 degree direction is the x-axis of the material coordinate system. What we're looking at right now is the material coordinate system for each element. Let's close this. So if you recall, that was going in this direction. That was the x material axis. But when we look at the element coordinate system, you can see that they're all going in this direction. Okay, so now let's look at what we have now. We need to take that stack and we now need to assign it to the cylinder. So let's go ahead and display that. Let's select the cylinder. It turns orange. Click the scroll wheel. Now the interface is going to change a little here. Now go to applies. Select the stack. So here, stack 1. Click add apply. Select the cylinder again. Click the scroll wheel. And then this is going to add a bunch of layers here. Now click on the zone icon. And then I believe at this point you should have a new panel here on the left. So let's go ahead and close this for a quick moment. I believe if you display the thickness, you will get something that's very thin, right? So it's very thin. Let me look here. I'm trying to look for my stiffener. Okay, let's zoom in. Okay, perfect. So that looks like the attribution was done properly. And let's turn off the thickness. Let's repeat this for the other stiffener. So let's go ahead and hide the other ones. So we'll go ahead and select the surfaces here on the left. Now, one thing that helps, you can change the background color. So let's go ahead and let's go back to panels and let's go ahead and add some additional stacks here. So we'll select this stiffener, click the scroll wheel, the interface changes, go to the applies tab, select the stack, click add apply, select this stiffener again, click the scroll wheel, click this icon here at the bottom left for zone. Okay, now here what you have, it shows you the direction. So here we're looking at the 1 degree angle, and then this is going to show you the 8 degree angle. So here you can see the ply, the one axis of the ply is going in this direction, whereas the one axis for this first ply is going in this direction. Okay, so let's look at this now. Let's go and repeat this for the other stiffeners. So let's go ahead and exit here. And then I think all my other stiffeners have been hidden. So let's go ahead and show them all again. Okay, so let's go back to panels. Let's select this, click the scroll wheel. Let's go to the applies tab. Let's select that stack from before, add apply. Select this, click the scroll wheel, all your plies are added, and then I believe, let me look here, I think I have to click zone. Right, I don't know if that last part is necessary, but I've just been used to it, so let's close here. And then let's see, what else do we have? Let's focus on this stiffener. So go back to panels, select this object, click the scroll wheel, go to applies, select this stack, add apply, select this, click the scroll wheel, and then here, again, I don't know if it's necessary to click the zones icon, but I like to do it. It's almost superstition at this point. Okay, let's focus on the last stiffener. So that would be this one here. Let's go ahead and go back to panels. Select this, turns orange, click the scroll wheel, the interface changes, go to applies, go to stack 1, add apply, select the stiffener again, click the scroll wheel, and then I believe we should have panels, right? Okay, so let me do this, let me close this, and let's go ahead and turn on the thickness. Let's go ahead and turn that on. Right now what I'm doing, I'm turning the mesh and the geometry on for everything. Let me turn off the thickness and turn on again the thickness. And when I zoom in, we can see what the total thickness of the layers are. Okay, now let's do one thing. Let's save. Let's export this. Let's call this, I don't know, I'll rename this actually, maybe C. Let me call this D Composites. So let's rename this. export. Okay, now when we go there, let's go ahead and open that new bulk data file. In the old bulk data file, we had something what's called a P shell entry. So if we look here, P shell, and let's go ahead and use that option. Oh, and no P shell entries. That's interesting. Oh, what's going on here? Okay, I think I'm just looking at the wrong file. Oh, there we go. Yeah, I was looking at a wrong file. So here, before we had one P shell entry that was used for all the elements. But in this new entry, we have what's called a pcomp or pcompg entry. So now here you can see, if you look at the angle column, angle field, this is going to be my 1 degree layer, 2 degrees, 3 degrees, and so on and so on. Later on, we'll change this to maybe 90 degrees, 0 degrees, -45, and 45, and so on and so on. Here, I didn't want to do that yet. I wanted to show you how the entries are configured. So this would be layer 1, layer 2, layer 3, and so on and so on. Now, as of today, it's May 2nd, 2025. I'm not aware Apex can display the layer thicknesses of the composite. So we're going to be using something called the SOL 200 web app. And we'll go ahead and open the viewer web app. Let's go ahead and upload that bulk data file. And let's go ahead and look at our model here. So here's the cylinder with the stiffeners inside. But here, let's go ahead and click on generate thicknesses. This is going to determine the thickness for each layer in the composites. So here, let me rotate this a little. So here, the cylinder has its own pcompg. Each stiffener has its own pcompg. If we look at the model browser here on the right, we can see all the individual layers. So here, let's go ahead and do this. Let's maybe look at this from this plane, the XY plane, and let's zoom in. And let's zoom out. So here, the stiffeners here, and then the walls here. Let's go ahead and turn on the layers. Okay, now let's zoom in very, very closely. And then while this is happening, let me run Nastran on that bulk data file. So if you look very closely, you see the individual layers for these composites that we define. Another thing, if you want to color coordinate the layers, as an example, maybe you want all the 90-degree layers to be colored the same. You can come here, click this button, and it's going to color coordinate all the layers the same color. So all the 45-degree layers will have the same color, all the 0-degree layers will have the same color, and so on and so on. Okay, so let's start wrapping this up. Let me see if I can do this. Or actually, I'm not. Let me do this. Okay. We're almost done with this exercise. Okay, perfect. So let's open this F06 file. Let's look for any fatal messages. If you ever see a fatal message, your analysis has failed, there's a problem, find that error, read that error, fix the error, try again. Okay, now there are no fatal messages here. If it's a statics analysis, I always like to look at this. I always like to look at the external work. Here I get some non-zero external work. This is telling me that there's deformation in this problem. Also, I get two rows or two values. This is the external work for load case 1, and then this is the work for subcase 2. Okay then, now let's go ahead and exit the thickness display. Here, if you go to the study tab, let me do one thing. Here, let's go ahead and save. Let's right click on, or before I do that, let's do one thing. Now, I want to update these stacks here. Let's go ahead and see if I can find it. Right. So here, I want to update these angles. So let's see if I can do that right now. I'm going to press insert on the keyboard. Let's go ahead and give this maybe 90 degrees. Let's go ahead and give this maybe 0 degrees. Let's give this 45 degrees. And then if you forget a decimal, that's not a good thing. Nastran looks at this number completely different than a number that has a decimal point. So just keep that in mind. Okay, let's go ahead and give this negative 45 degrees, 90 degrees, 0 degrees, and then here, let's go ahead and keep looking here. Did I do this right? 45 and negative 45. So save that. You could rerun the analysis. Alternatively, you can come here in Apex and you can do the edit manually here. So here, double click on panel 1, go to applies, and you can do that here. So you would double click here, you would say, okay, this is 90 degrees, and then there's a delay period here. So here 0, and so you can see the process is a little time consuming here. I think this is what I'll do. Let me do one other thing. Let me zoom out here. Let's see, let me turn all of this off. Okay. Let me zoom in here to this bottom stiffener. Now back in Apex, let's look at the shell normal. Let's change the color and go back to shell normal. So remember that our normals look like this. Let me display all the stiffeners here on the left, turn on all the surfaces, turn off the normal and turn them on again. Oh, I have to display the elements also, so let's turn on the meshes. And let's zoom in here at the bottom. Remember, the normal determines the direction that you stack your layers. So this is layer 1, 2, 3, 4, and so on and so on. In the viewer web app, you can look at that. So here, let's turn on layer 1. For this, I have to zoom in very closely. So this is layer 1. And let me zoom in actually to the wall maybe. Let me try and get the stiffener up here. Okay, so this is layer 1. Layer 2 is on top of that. Layer 3 is on top of that. It's very subtle here, but you can see that the layers are being stacked. So here on the model browser tree, we'll go to gply 4. We'll turn on the checkboxes, and then that turns on the 4th layer, and then we'll do that again. So layer 5, layer 6, layer 7, and 8. So here, what I wanted to prove to you is that the layers are in fact stacked along the normal direction of each element. Okay, now one quick thing about this tool. There is a first-person mode option. So hey, if you like to game a lot, if you like to play video games as we called it a long time ago, here, give me a moment. I'm using a virtual machine, and sometimes the mouse likes to act up here. So let's go back here. So when you go in this mode, you can navigate the model like a game. So here we're inside of the actual cylinder. If I look behind me, I look at the other edge, and then if I look down, I can see that cylinder. Suppose I want to go inside of this reinforcement. I can go here, and let's go ahead and go in a little. So I'm inside the reinforcement right now. If I want, I can move sideways. Let's go ahead and exit first person mode. Let's see, what else did I want to show you? Let me think for a moment, because in a moment we are going to be talking about something else. Okay, let me see here. Let's now do this. Let's now change the angles to 90, 0, 45, and so on and so on. So for this, let me look here. Let's go back to Apex. Let me delete all the panels we had before. So we'll delete this. We'll delete this. And this. Okay. So let's go back to our stack and do this. Let's change all of these again. So this is going to be layer 1. We'll say use 45 degrees. Layer 2, that's going to be using negative 45 degrees. The next one is 0 degrees. The next one is maybe 90. And then here 45 and negative 45. And I'll do this again and again. Now, I deleted all the other composites that I've defined because I don't know how to just edit in place quickly. So to me, it was easier just to delete everything and do it again. Okay, so here, what we're going to do, we're going to also make this symmetric. So here I defined 8 layers for one side of the line of symmetry. And when I turn on this checkbox, it's going to add an additional 8 layers for the other side of the line of symmetry. So that's what that looks like. Okay, now let's go back and open it again. Okay, the stack has 16 layers. Let me make sure my angles look okay. Okay, 45, negative 45, 0, 90, 45, negative 45, 0, 90. Okay, let's go back here and turn off the element normals. And let's turn off the cylinder for now. Let me see if I can do this all in one go. Let's select panels. Let me go ahead and do this. Let's go and select all these. I don't know if I can do that. Let's try. Hold the shift key, and what I want to do, I want to see if I can select multiple. Oh, I guess I can't. Okay. Let's press the escape key. Okay, let's go ahead and click that one. Press the scroll wheel. It's called MMB or a middle mouse button sometimes. Okay, let's go here. Stack 1, add. Press the scroll wheel, and then I should have a new stack here on the left. So for part 4, I have a new stack. Let's go ahead and close this. Okay, so now let's go to part 3 and do the same thing. Now, while I'm doing this, I think the initial discussion on the material and coordinate systems was not clear. So what I'm going to do towards the end of this video, I'm going to give you a better example. So we're almost done. Just hang in there. I'm just assigning these composites to these individual parts. Okay, so now I have another panel here on the left. Let's go ahead and close this. And now here, let's go ahead and focus on this next stiffener. One thing you can do is, say you zoomed in very closely, you can press both the left key and the right key on the mouse, and it's going to put everything in the view. Okay, so now let's focus on this stiffener. So let's pick this object, click the scroll wheel, click plies, select the stack that we want to apply, click add apply, select this, press the scroll wheel, and now we have our next panel created here on the left. Okay, now let's go ahead and close this and move on. You know, while I'm doing this, I just realized that, you know, I think I'm just going to create a separate video about the element and material coordinate systems. So after this video is done, I'll just go ahead and create a new video. Let's make sure we're in the right spot. Okay, so this reinforcement or stiffener, go to applies, select the stack, add, select this one, click MMB. Okay, and let's just wait a moment for this to be done. And I know it's working because that cursor was showing me a little wheel. I was waiting for that to finish, and now once that's done, I'll carry on. Okay, so let's create one last panel for this composite cylinder. Press that, it turns orange, click the scroll wheel. The interface changes a little. Go to applies, select the stack, click apply, select this cylinder, click the scroll wheel, and now we have the last panel. Let's go ahead and close this. Of course, we have to wait until this wheel stops spinning. So now it's doing its update. Let's close this. Let's save this. And now let's export. So we'll go ahead and call this model E. Export, and now let's go ahead and go back to the downloads directory. Let's open this in Notepad. And let's look for pcomp. So in these new pcomp G entries, I expect 16 layers. And I expect it to be symmetric. So 45, negative 45, 0, 90, 45, negative 45, 0, 90. So this is one side of the line of symmetry, and then we have the mirror side, if you will. So now it's in reverse, 90, 0, negative 45, and so on and so on. Okay, let's go ahead and do this. Let's reload the viewer web app, and let's import this new bulk data file, model E. And now let's go ahead and run Nastran for model E. Okay, and let's generate the thicknesses because we want to actually look at what the new thicknesses look like for each layer. So like before, we'll go ahead and zoom in very carefully, or I think what I'll do is I'll rotate this a little. So let's go ahead and rotate this, and let's zoom in very carefully. And here my computer is going to run a little sluggish. Okay, let's go ahead and turn on the G-plies as they're called. And here I'm still too far away. Let's zoom in a little closer. What I'm doing here is I'm hiding the plies first, and then I'm zooming in. This is a web browser. You don't want to overload the browser with a lot of visual objects, rather. So here I zoom into where I want, and then I turn on the plies. And right now you'll notice that each layer gets a different color. If you click this button here under column color of detail, now I know this. All the positive 45-degree layers are blue. All the negative 45-degree layers are green. All the 0-degree layers are yellow. And all the red layers are 90-degree layers. So you can see all the layers for the cylinder wall and the stiffener that we had here. So if we move along this, you can see what that looks like. And then if we zoom out by clicking on Fit Model, this is what our stack looks like from a far view, if you will. Okay, so let's go ahead and do this. I think we're almost done. So let's go ahead and look at the F06 file. As always, let's look for any fatal messages. So fatal message, there is 0 fatal messages. That's good news for us. Let's get a quick look at the external work. Okay, perfect. That looks good. Great. So now let's talk about the results. So we go in the study tab. Let's look at the deformations here in the study tab. So we'll right click on scenario and attach the results. And here, let's go ahead and attach model E, H5. Right, okay. Now, the viewer also has its own post-processing capability to look at the results. So here we'll go ahead and upload the H5 file. And now here in Apex, we'll go to the results view. And we'll take a quick look at the deformation. Remember, the whole goal of the video was to get radial expansion in the cylinder. We'll see if we were able to achieve that in this. Okay, then here in the viewer web app, I'm going to do this with the viewer and the post-processor web app. One thing you'll notice, the scale factor for the deformed shape is just too high. So let's bring that back down a little bit. Maybe we'll scale it by 0.1. It's still too high. Let's go ahead and give this a value of maybe 1. Right. 1e negative 3. You'll notice one thing in my deformations. I'm working with units of meters. If you look at the top of the bulk data file, you get told what the unit system is, if you will. So here, let me copy this here. You get told that this file was created with the unit system of meters, kilograms, newtons. One quick comment about units. Throughout this exercise, all we cared about is running this with Nastran. It doesn't matter if you use Patran or MSC Apex or some other tool. You need to run it with Nastran ultimately. Nastran is like a calculator. Your calculator doesn't know what units you're using. It's up to you to handle the units. It's up to you to carefully manage the units. Here, when you look at this bulk data file, there's no notion of units. It's like when you do your math homework on a piece of paper. The piece of paper, your calculator doesn't know what units you're using. You, in your mind, is where the units live. You are responsible for that. Now, outside of Nastran, outside of the calculator, Apex does have a notion of unit system. So you can switch between unit system, and Apex will take care of the conversion, if you will. Okay, now the reason I mentioned that is because the cylinder had a diameter of 3 meters, I believe. But if you look at the deformation here, the deformation at most has a deformation of 2,000 meters for a 3 meter cylinder. That's a very big deformation. There's something clearly wrong. This is what's wrong. If you remember back when I created the orthotropic material for our make-believe carbon fiber, the Young's modulus for the 1 and 2 direction was very small. This is a very soft laminate, if you will. The layers are soft. So when I give this a pressure, the deformations are very, very large. So here, if I were to use more accurate mechanical properties, I wouldn't get such a high deformation. But here, what I'm doing is I'm going to scale it. So let's go ahead and scale this a little. Okay, so this is what the deformation looks like if you scale this horribly deformed cylinder. So this is what that looks like. One very important detail about this, you can see that our cylinder is actually expanding. So we'll turn that off and we'll turn it on. Maybe let's go ahead and give this a different scale factor. Oh, that's too high. So let's go ahead and give it maybe 4. Let's try 5 here. Right, so this is before deformation and then after deformation. That's what that looks like. Okay, now we can do the same thing in Apex. So let's go ahead and look here. Oh, what's going on? Let me see if I can attach the results. Oh, that was weird. I thought I attached the results a moment ago. So attach. Okay, something is going on here. Normally there would be a button here that says look at the results. Attach results. Model e.exe. Okay. Oh, that's interesting. Let's see. Let's do this. Let's close Apex. I think eventually when you use a desktop application for more than 2 hours or so, eventually there's a conflict that happens in the application, so you have to close and restart the application. So what I'll do now is I'll reopen Apex here, and I'll let that happen in the background. What I wanted to show you in Apex was this deformed plot. Also, I wanted to show you the apply stresses. So here, let's select a different data set here on the top right. We'll select the element stress quad 4 comp data set. We'll select the first subcase. And we'll let the browser go ahead and acquire the data for that load case. So here you can see that feedback here, acquisition in progress. This will go fast or slow depending on how big the results are. If it's a lot of results, it might take a minute, maybe 30 seconds. If it's a small model, it'll just take a few seconds. So we'll go ahead and give that a few moments. And let's go ahead and see where Apex is at. Here, let me just wait a few moments here for the web browser. And one quick thing, things are going to go slower in this video. I'm actually using what's called a virtual machine. So let me see if I can show you that. So here, my main machine is actually Ubuntu Linux. And what you see now is a virtual machine of Windows 10. So this virtual machine has 2 processors or 2 cores and about 400 or 4098 megabytes. So there are not a lot of resources. Things are going to go a lot slower in this virtual machine, if you will. Okay, once this says acquisition complete and successful, let's look at the apply stresses for layer 1. So this is going to go ahead and prompt the web app to go ahead and plot the layer 1 stresses. Now that's what that looks like. Now you might be asking, let's turn off the deform shape. You might be asking, okay, I know I'm looking at the stresses for layer 1 in the one direction. What does the one direction look like? You can use this option, display directions, and then this will show you the 1-2 axes for that layer. So here, I forget what orientation is that one. So let's go ahead and look at this. I think it was positive 45 degrees. Right, so the first layer is positive 45 degrees. Let me go ahead and look at this from a different direction. So let's see if I can get this to work. And let's zoom in here. Oh, right, so it's going to be on the other side. Okay, let's do this. Let's go into gamer mode. Let's go into first person mode. Okay, let's go into gamer mode. Let's go ahead and go inside the cylinder. Let's go ahead and rotate this. And let's look to the side. Okay, so this is the one direction of the 45 degree layer, or layer 1. Right now we're looking at the normal one direction. So this would be the apply stress along the one direction of the 45 degree layer. Let's look at the Y1 stress. So here I select the Y1, which is the normal 2 stress. So it's not visible here, but it's there. So if this is the one direction, the 2 direction would be perpendicular to the one direction. So the 2 direction is along this direction. So now let's go back and display the stress in the one direction. let's look at the stress in the layer 2 direction, which was negative 45 degrees. So this is negative 45, this is 0 degrees, 90 degrees, and then it's repeated. 45 degrees, negative 45, and so on and so on. Okay, so now thanks to the color difference, here the green axis, that's going to be the 2 direction of your layer. So let's go and jump to a different layer. Let's see if we can do it. Okay, so here this looks like it's a 90-degree layer. Your apply stress is going to be in this direction, and your 2 stress is going to be in this direction. Now let's go ahead and do this. Let's move around here. Let's do this. Say you want to know the maximum apply stress for all the layers. What you can do is you can click and hold all the layers here on the right. This is going to determine the maximum apply stress. And suppose you want to know where the maximum apply stress is. Here, you get this maximum label option. Select the first 3 options, if you will. And here, let's go ahead and turn off all the directions. Here you can see that they have been superimposed. And then while this is happening, let's see if Apex opened. Oh, it seems like we may have had an issue. Oh, right. I think since the web browser is taking a lot of resources, and since I don't have a lot of memory, I don't have a lot of processors, other applications are going to take a lot longer to open. So that's why this other application was taking a little longer. Okay, now back here, we turn on the labels for my maximum apply stress and my apply strain. Let's see if we can figure out where they are. Okay, here they are. So let's go here. Okay, so here I get some information. These apply stresses are the highest out of all 16 layers. I get told what the maximum apply stress value is. Here it's a 3.63 or 36,000 pascals, if you will. As for the element ID, it tells me the element ID and it tells me the layer. Here in the right-hand side, let me highlight that for you. I get told where the maximum and the minimum are. It's the same information. So this is what we'll do. We'll select layer 14, and then we'll turn on the direction. So here, because the color plot is also red, it's kind of blurring the 0 degree axis. So this is the one direction of the apply. So we know that the apply stress is in this direction. Let me do this. Let me actually take a screenshot of this, so you see what's happening. So right now, this is showing me sigma 1 for the, let's see, what layer is 14? So this is layer, I know this is layer 16, 15, and 14. So this is going to be a 0 degree layer. So this is going to be sigma 1 for 0 degrees. So let me give this a different color. Maybe not blue. Let's see if we have black, right? So this is going to be in this direction. So this is sigma 1. For the other elements, this is going to be sigma 1. So now we're looking at the values for sigma 1. And we get told that these 3 elements here have the highest apply stress out of all 16 layers. Now, what if you wanted to look at sigma 2? If you go back to the viewer web app, you change the field to Y1 normal 2. And then now you're looking at the stresses for Y2. So basically the stresses along the 2 axes of the apply. Okay, now here in Apex, maybe it's worth showing, I don't know. Okay, now I'm getting a little confused. I don't know if it was model. I don't know if it was this model, but we'll see if it opens. Okay, What else is there to look at? A few other things you can do here. You can look at load case 2. So here, if I mark this checkbox for load case 2 or sub case 2, this is going to go through that whole process of getting the results from the H5 file. So the web browser is accessing a copy of the H5 file. It's opening the H5 file, it's getting the results, and it's bringing those results back to the web browser. Now here, oh, this was the wrong model. I forgot this model was here, so we'll have to censor that in the final video. Let me see if I can find the right video. Okay, let me look here. Let me try to figure out where that old Apex copy was. Okay, so I think it was this one. So it was model 3. Okay, so we'll let that open. Okay, so here we get acquisition complete and successful. You then select the layer and then you get the color plot. Let's go to an exit first person mode. Now let me repeat this. So we're looking at load case 2. We marked this checkbox. We waited until this said acquisition complete and successful. We want to look at the stresses along the one axis of apply. Let's select all the layers here. Let's turn on the maximum label. We get told it's in layer 14. So that would be here. I think this makes sense. Your cylinder is going to deform like this. It's going to look like a saddle for a horse. So if it's going to saddle, this stiffener is going to be elongated, if you will. So that could potentially be causing the high apply stress that we saw here in this reinforcement. Okay then, where are we at now? Right, so here let's do the same thing in Apex. Now, I don't want to talk about this too much. Here, I want to show you one last time how to attach the results. So you go to scenario 1, you select the H5 file, you attach. And then here, I think one thing I forgot to do, let's go ahead and place this in the analysis scene. I think that's what I might have forgotten. Oh, and I guess it still doesn't work. Okay, unfortunately with Apex, I cannot show you the results in Apex, but that's okay. You saw that you can see the same results in the Viewer web app. If you're a student, or actually, if you use MSC Nastran, the Viewer is free for you to use. So if you want, you can go to theengineeringlab.com. You can click on free download for the post-processor web app. You can see both options are free. Fill out your name, email. Gmail is not supported. So if you try and use a generic Gmail address, this is not going to work. I encourage students, professional engineers, and researchers, use your personal email address. We don't do any marketing activities, so don't get worried that your data is going to be in some marketing database. We actually don't do any marketing, surprisingly enough. No email address is retained. We don't send blast emails. I think that's one unique thing about this startup. We don't do marketing. Okay. We only do training tutorials like the one you're seeing now here on the desktop. Okay then, I'm pretty much at the end of this exercise. Now, I rehearse this for 10 minutes. I use Apex maybe once every month. I don't use it that often. So apologies if this tutorial was a little rough around the edges. If I could do one thing a little differently, I want to give a different discussion on the material orientation field. I think this is very important if you're new to Nastran. So what I'm going to do is I'm going to create a separate video and talk about the material orientation in a separate video. But hopefully you found this video useful. Let's do a quick recap. We did a lot. What we wanted to do in this exercise, and let me see if I can find it. We wanted to do the following. We had a cylinder with reinforcements or stiffeners. Both of these were created with the composite laminates. We had some pressure, and we wanted to allow radial deformation. So we did that. Let's see what else we do. So there are dozens, maybe hundreds of different ways to connect your parts together. One of the easiest ways was permanent glue. If you're new to Nastran, permanent glue is typically one of the easiest ways to attach your parts together. But later on, you have other ways. You have C-Bush, C-Fast, and so on and so on. These take a greater level of skill, so this is why I didn't do that in this exercise. Permanent glue is a great way if you're new to attach your parts together, if you're new. Also, remember, everything you saw here took me months to learn. I was learning how to use Nastran back in 2009, back when I was 19 years old. So it was a multi-year process, multi-month. Thankfully, tools are more advanced. We could create this very elaborate model, and here I'm thinking we're up to 2 hours with the training tutorial. The steps I showed you took 2 hours, but learning the significance of each step will take days or weeks. So again, if you have a deadline that's coming tomorrow, I suspect you're not going to make that deadline. If your deadline is in a few weeks or a few months, great. This tutorial will definitely help you move towards your final goal of getting your model. Okay then, I think we're pretty much at the end of the video. One last thing, say you eventually want to perform a composite optimization. We also provide, it sounds like I'm selling the tool, but I'll say this. If you want a tutorial for composite optimization, you can go to theengineeringlab.com. You'll find multiple examples. If you want to perform a apply number optimization, we have one devoted to just that. Let me find it here. Apply number optimization. We have so many tutorials that sometimes it's easier just to search the whole page. Here we go. So there's actually a tutorial that will show you how to perform apply number optimization. So here we show you all the steps that you need to take. Where do you click? What do you select? How do you constrain apply stresses maybe? How do you define apply number variables? That's all included here. Now, if you have optimization questions, if you have machine learning questions, you can contact me at this email address. Now, Nastran is a very big program. Very often you have not hundreds, but maybe dozens of users, dozens of developers, hundreds of other individuals that are using the product. You have error elasticity, motor frequency response analysis, buckling analysis. This is a lot for one organization. So our organization is focused on just optimization and machine learning. So if you have a question about optimization and machine learning, you can contact me at this email address and I'll try and get back to you as soon as possible. So with that, I'll end the video here. And like every other video I do, I always like thanking you for watching it. So thank you.